In this video, we look again at the importance of the order of integration in a problem, and maybe the importance of maybe possibly even reversing the order, okay, and why this is important. Okay, so we can see here an example problem that has been set up for us. A lot of plots have been given to us, a sketch of the region. We can see that we are being asked to find the volume, okay, and a surface has been given to us, and that surface has been given to us as a function of x and y, okay. Down here in the xy plane, we have a particular region, okay, and we are trying to find the volume above that region in the xy plane, right, but below the function given by the surface, or below the surface given by the function, I should say. Okay, now they've given us some information about this region. They say the region is bounded by the curve y is equal to 2 square root of x, and is also bounded by the line 4x minus 2. Okay, so what we're seeing here, down here, is a plot conveniently given for us, the line 4x minus 2. We can see that 4x minus 2 is equal to 0 when x is equal to 1/2, which is why that line intersects the x-axis at 1/2. And we also have the square root function, 2 square root of x. Okay, and it's possible to see that the 2 square root of x function intersects the line, right? Maybe we would need to square both sides. So it'd be 4x is equal to 4x minus 2 squared. 4x, expand this out. So that'd be 16x squared minus 16x plus 4. Okay, so that would lead us to 16x squared, let me see, minus 20x plus 4 is equal to 0. And you could use the quadratic equation, okay, and figure out that when x is equal to 1, that would be 16 times 1 squared minus 20 times 1 plus 4, that does in fact equal to 0. So that's why we are seeing these graphs intersect at x is equal to 1. Okay, now that we have the order, the kind of the edges of this region laid out, we know some intersection points. We would have to decide on what order of integration we would want to do for the volume problem. Okay, now there are two choices, right? We're trying to do the double integral of a function dA over a region R, and there are two choices for dA. That is either the dx dy or the dy dx. And it would be possible to set up both of these. You just might need to be a little careful about it. Okay, so people typically like to think in terms of y. This is how we're most used to thinking. So if you were going to set up a y integral, right, do the dy dx ordering, that we would have 16 minus x squared minus y squared. That is the function. We'd want to do a dy integral, and that means that we need to do the bottom function and then the top function. And what we can see here is that the bottom function is the bottom edge of this region. It is y is equal to 0. So y goes 0 up to that 2 square root of x function. Okay, so we could say that the bottom would be y is equal to 0 up to y is equal to 2 square root of x. But something happens so right, you keep moving over for different values of x, and the bottom is still y equals 0, and the top is still the 2 square root of x function. but at x is equal to 1/2, right? So now we need to do the dx integral, and the bottom y equals 0 is only the bottom function when x goes from 0 up to x is equal to 1/2. So that is the only values of x where y is equals 0 is the bottom function. Something important happens after x is equal to 1/2. We have a new bottom function. Okay, so what we would need to do is to split this integral up into two pieces. So if you try the dy dx ordering, we would also need to add on some volume, and then that would be y going from 4x minus 2 on the bottom, the line, up to y is equal to 2 square root of x on the top. 16 minus x squared minus y squared is the surface. And now we're still doing the dy dx ordering, but 4x minus 2 is the bottom function when x reached 1/2 up to x is equal to, and since we know the point of intersection, we can say that that's x is equal to 1. So if you want to do the dy dx ordering, you're going to need to do two double integrals. Okay. Well, the convenient thing about being able to switch the order of integration is that there is a big or here that you can do the double integral. You can do this as a dx dy problem. We still have the function surface that we're trying to find the volume under. And then we would want to do the dx dy ordering. And then now we need to go and turn this into a left-right problem. Okay, so the left-right problem is what's on the left and what is on the right. And the convenient thing here is that the function that's on the left is the square root function. So when you solve 2 square root of x, y is equal to 2 square root of x, solve that for x, you get y squared divided by 4. And then what's on the right is always the straight line, and if you solve that straight line for x, you get y plus 2 divided by 4. And that will be true for the y values, okay, always between 0 and 2. And you can check that, for example. So probably something interesting to note here is that when y is equal to 0, okay, we can see that the straight line will be 0, 4x minus 2, x is equal to 1/2. So when y is equal to 0, you are at an x value of 1/2. But when y is equal to 2, you know you have the right upper limit here when you should get an x value of 1. So if we check that now, if y is equal to 2, 4x minus 2, where does that line put us? It puts us at 4 is equal to 4x, x is equal to 1. So we know we have the right y region here with a little bit of algebra. So now we would have two choices, two different integrals to evaluate, and we can check that now and make sure that these integrals compute to be the same thing. So let's just check and see what the answer is going to be. Let's do the easiest one first. Let's only type a single integral, the dx integral first. And then we had 16 minus x squared minus y squared. So I will leave you to check the evaluations by hand. Okay, y was going to go from 0 up to 2, and then x was going to go from y squared divided by 4 up to y plus 2 divided by 4. Okay, so let's put the y plus 2 in parentheses. Right, so the answer you should get would be this fraction. If you convert that to a decimal, 12.3827. Okay, so let's check, just make sure that we get the other order of integration. We would have to have two integrals to do that one. So we have this to fill in, and then we're going to add another copy, another double integral. Okay. We're going to do the same function. So we'll put that same function in both places, I hope. Right. Now, the y limits 0 up to 2 times the square root of x. And then that y equals 0 was the bottom function only from 0 up to a half for the x values, and we had done the dy dx ordering. Now, for the dy dx ordering, there was a second integral to bring in, and that would be x going from 4 times x minus 2, the bottom function, up to 2 times the square root of x. And then we would have to go from 1/2 up to 1. And if we compute both of these integrals, the hope is that they give the same decimal answer. Okay, 12.3827, 12.3827. Okay. So you can see that they evaluate to the same decimal. That's a good thing. But if you were using the symbolics to compute them, we can see here that these answers don't quite exactly look the same. But if you were to simplify them, they would simplify to the same answer. Okay. So one important thing I want to do here is just to show what we have done geometrically with these two double integrals. Okay, and I just want to show here again a region plot 3D command. That what we have is we're going from 0 bigger, z is bigger than 0, and z is below the function, below the surface. Okay. And we want y to be bigger than 0, and we want y to be less than 2 times the square root of x. Okay. So I'm just typing in these limits of integration, right? Just kind of putting them into a region plot version form. And then let's see, x had to be bigger than 0, and x had to be less than 1/2. Okay. Now we need to show the region. We need to pick the values of x and y. And let's look at this region here. We can see, let's just look at a rectangular region. X going from what we know from this picture, x going from 0 up to 1, and y going from 0 up to 2. Okay. And since it's a region plot 3D, we also need the z values. Let's see if we can see what our picture was doing. It looks like the z values go up to about 16. So let's go z from 0 up to 16. Okay. Now one thing that's interesting here is that you will see, okay, we can do more plot points to kind of make this look a little bit more. Okay. So what we're seeing here is only part of the region. Right? It's the part of the region that is over this first kind of triangular piece, and I think that's what we're seeing here. If you look at this from the top, it's the triangular piece. You can put an axes label, goes to x, y, z. Oops. Okay, and we can give that plot style goes to red. Okay, so now there is, and we can call this plot 1. But there is another part of the region, right? And we can call this plot 2. Okay, and it's the part where y is bigger than the line 4 times x minus 2. Okay, and that was when x was bigger than 1/2, but x was less than 1, and everything else and let's call this blue. So now we have two different regions and we can show them together. Okay, and we can see that, oops, sorry, P2 wasn't defined. Okay. And here we have, for each integral corresponded to a different color. Okay, so this first integral here, that is the integral in red, and then we had another integral that was in blue. Okay, and we can see here that if we look at this from the top in the xy plane, we have two different regions, x going from 0 to a half, y going from 0 up to the top square root function, and then the next integral was x from a line up to the square root function. And if we bring in the three-dimensional aspect, we can see that we're finding the volume that is below the curvy surface, which is part of the paraboloid. So ends this video.